And we can have now Matthieu.
Do you guys
Okay.
see my screen?
Yes. Okay, so
Okay.
you can start.
Okay. So I apologize. I changed the topic. I was planning to discuss diffusion models, but actually I would really be discussing the last question that was raised by Bernd, actually, which has to do with scanning laws in large language models when you actually learn features. And yes, so that's going to be related. And it's not really a survey, so I'm going to survey questions that are interesting to us, and I think to much more broadly to this group. But I decided to sort of take two works as a sort of example of how we attack those problems. And I have to say that the first author of those works is Francesco Cagnetta, and he's one of the organizers of this webinar. So actually, if you have questions in the chat, he could answer them. And if you have questions of broad interest, please interrupt me, and I would be happy to actually stop. Okay, so that's a slide to the broad question that puzzles us is the so-called curse of dimensionality. Just the fact that in large dimension, you should not be able to learn. And this is coming from a very simple geometrical fact. Those little crosses here are data in large dimension. Even if you gave me many data, so in this talk, P is a number of data. In large dimension, the distance between them, delta, just decrease like P per -1/d, where d is the dimension. So if the dimension is large, it means this is not decaying essentially. So you can't sample space in large dimension. And because of that, you can show, for examples, for supervised learning, but it's also true if you do unsupervised learning, you're trying to learn a distribution. But for example, for supervised learning, if you assume little on the task, say you're regressing a function, which is just Lipschitz or something like that, the only way you can do this properly is by, making this distance between points to be small, which require an exponential number of data in the dimension. And clearly, it's not going to be possible. I mean, if you think about images and so on, you live in too large dimension to actually do that. So the fact that deep learning and actually our brain can deal with data in large dimension must imply that actually those data or the task have a lot of structure. And really a question which many are interested in, it's central to our group, is, what is the nature of this structure? How do you think about it? And then related question, how deep nets, for example, can exploit this structure? So it's widely believed that the success of deep learning has to do with the fact that they build an interesting hierarchical representation of the data. So this is an example. If you train a network on ImageNet or something like that, after training, you can look at what neurons mostly respond to. And you find that maybe in the first layer, they respond to low-level feature of an image, like an edge or something like that. But as you go deeper, you have neurons that specialized in very abstract aspect of an image, like, a face, having a face of a human or something like this. And this hierarchy of representation is also believed to be there in our brain. It's a beautiful observation. And at an intuitive level, you may think that it's good to have a representation like that because maybe essentially what you're doing is lowering the dimension of the problem, and so you make it tractable. But then the question is, how do we learn those representations? So the specific question I want to think about is, how many data do you need to learn such a hierarchical representation? And how does it depend on the task and the data itself? Okay, so and in the first part of the talk, I will be thinking about supervised learning. But then I want to think about language model and self-supervised learning. For example, when you mask a token and you ask a machine from the context, from the rest of the text to fill up a blank, guess which word or which token was there. And then again, the question will be, under which condition can I build a hierarchical representation of text? It's believed that, I will come back to that in a few slides, that a key aspect, at least of the level of a sentence of text, which is also hierarchical, is the grammatical structure of text. And so this question of learning a language is actually about, a very controversial question of linguistics. How do you learn languages? And it has been argued by Chomsky and co-workers that actually it should be impossible to learn the grammar of a language just from examples, because it's very degenerate. Even if I give you millions of sentences, there are many different grammars that can actually fit that. Then there are alternative views that, in fact, maybe quite generic neural mechanisms have an implicit bias towards specific grammar, like interesting hierarchical grammars. And that those can exploit correlation in the data to actually build a hierarchical representation. And there are evidence for that. I don't have time to review this literature. Obviously, what we now know is that large language models, just from examples, they do an amazing job in actually learning to speak, learning the grammar, but they need a lot of data. So what's understood about that? What's known, there are many studies that show that after training, if you look what those transformers are doing, actually they do capture some aspect of the hierarchical structure of data, for example, grammar. But again, what's not understood is how do they acquire it? Again, how many data do you need? And related to the previous question, what correlation in the text can you use to build this hierarchical representation? So that's the focus of this presentation, learning hierarchical representation, but it's completely related to the question that was previously discussed, which is scaling laws, right? So one way to characterize performance is to show the training curves. They tell you, for example, the tester, you would like this quantity to be as small as possible. It's epsilon here as a function of the training set size. And typically what you find for many data sets is that eventually this is decaying as a power law with some exponents that I call beta here. And this exponent can actually depend on the data you're looking at. But the key point is that naively, this curse of dimensionality idea will imply that for generic tasks, this beta should be over the 1 over d. So essentially 0, you should not be able to learn. And that's much larger than that. So in this presentation, I will be talking about power law, scaling laws, this exponent beta, but I have in the first part of the talk another way to actually characterize success. It's sample complexity. So what you do is instead you fix some level of error, epsilon, tester, and you ask, what is the data, the minimal number of data I need to reach such an error? Okay. In this talk, it's P star, the sample complexity. Say epsilon is 10% or something like that. Okay, but we want to think about theories for large language models of scaling laws, fixing those exponents, and how do those theories, we would like to essentially describe scaling laws and in the same time, how you learn hierarchical representations. So in the first part of the presentation, I will be discussing data structure and introducing a very simple model, which still captures the hierarchical nature of data. Second part, that's going to be about supervised learning. And then the last part is about next token prediction. And we'll have a theory and we test it on Shakespeare and Wikipedia. You will just have Shakespeare today, actually. So that's the strategy. So the viewpoint that a lot of the theories that's currently going on is assuming the least on the data, which is sort of natural. I mean, that the data are Gaussian or maybe a mixture of Gaussian and something like that. So we think that we need simple models with much richer structures. As we are all physicists here, we know that simple models, even if they are caricature, can be useful. But it's important then to empirically test if those models actually capture something of the real data. We use a good, empirical method. So here I will introduce a model, and then, the goal is then to work it out and have predictions that you can test for real data. Okay, so that's going to be the slide that motivates the model that comes on the next slide. And this model, we would call it the random hierarchical model. And essentially what we seek to capture is the fact that data can be compositional, hierarchical, and also have some kind of local property. So maybe it's true for text and images, but say, let's think about images. Compositional is just that, for example, a dog is made of a head, a body, and limbs. Hierarchical because the head itself is made of eyes, nose, things like that. So and also local properties, the fact that pixels that are close together or tokens that are close together make sense together. And I mean, one of the fields that has thought about data structure the most, I believe, is linguistic. And in particular, you have beautiful classification by Chomsky. And he argues, the sort of dominant example of his classification, is that one should think about text. I mean, it's just about structure and grammar, but that you should think about text as being generated, produced by a generative grammar, which is essentially a tree. And then what you have to describe is the rules that build the tree, and they are called production rules. I will give an example. Our model is an example of that. But this idea that you have a tree underlying data, as is also popular actually in the context of images, for example, it's called pattern theory. And scientists did try to label images and build grammatical trees, decomposing images in pieces and sub-pieces and so on. Okay, so what I'm going to do in what follow is trying to come up with a very simple model. So we'll use two actually simplification that have been introduced in the literature. We will put them together. I mean, the first one is to assume that the tree is fixed in topology, okay? And the second one is going to assume that I told you that there are some sort of dynamic production rules that tell you how the tree can evolve. We'll assume that they are random. And thanks to that, we'll be able to compute essentially all correlation. I mean, you can compute in principle multi-body correlation in this problem. But essentially, we will create a generative model. And this generative model, it can give you a bunch of data, which come with the label Y and the data X. So you can think about supervised learning, you know, how a machine will try to learn Y from X. But also it comes with an interesting distribution of the data itself. So the distribution P of X is itself hierarchical. And so you can study self-supervised methods based on those models. Okay, so this is a slide where I introduce this model. So you can stop me and ask me a question if it's not clear, because the rest may be hard to follow otherwise. So, so essentially, it's a generative model. We will activate it and generate one data, one at a time. So the first thing you do, maybe you could first look at the tree over there. You're going to choose the class. Maybe you have cats and dogs. Let's randomly toss a coin, choose one. Let's say one is a dog, something like that. Then what the model is going to capture is the fact that that a dog is compositional, is composed of several things, like a head and a body or something like that. So in the model, we capture that by saying that each class one is composed of a certain number of features, which is S. S is an important parameter in what follows. And in this example, S is 2. It's just the branching ratio of this tree. Those different features, for example, in this example, A and B, they are taken from some vocabulary of size V, but that's not super important. And the vocabulary, even for simplicity, is disjoint at different levels. So when I will go down later on, I can't find A, B there. Okay, one key parameter, maybe the most important in this model, is the fact that a dog doesn't have just one way to be decomposed into features, because otherwise the model would be stupid. It would just be always the same dog. Only one data would correspond to a dog. But dog could be of different species, in different orientation. So it's degenerate. So we assume that you have M different strings that actually encode the dog, and they are synonyms. So for example, in this example, if you look on the table on the left, if you have the class 1, it can be encoded by AB, AA, and CA, something like that. And when you decide to produce a dog, you choose one, and then you're going to randomly choose one of those three guys, AB, AA, CA, with probability 1/3. So how do we choose, the set of strings that go for the dog and the set of strings that go for the cat? Well, they're just random set of strings, but they have no overlap. So there is no confusion. In this model, a cat can never and a dog can never be confused. And then we're going to repeat what this process L times. So L is just the depth of this little tree that you see here. Okay, so at the end of the day, those kind of models, I mean, technically, for those who know about this linguistic aspect, I mean, this is a probabilistic context-free grammar. So what you need to specify are those production rules, all those tables, and then when it's easy to generate the data, you toss a coin, decide one or two, say you decide one, randomly you chose A, B, then A you chose randomly E, F in this example, and B became D, F, and so on. And at the end, you got this data in green associated with label one. But you can generate many data. So the dimension of the strings that you generate obviously is just as the branching ratio power L, which is the depth of this generative model. But the number of data you can generate because you compose, you make a bunch of independent choices is exponential indeed. So you can generate a huge number of data with that. Are there any questions on the model?
I just have a quick question. Probabilistic context-free grammar is, of course, a much too simple model of actual spoken language. We use that for, generating faux text sometimes. SciGen was a famous example of that. And, that's not a problem. You're just, you're trying to model something. But my question is, or maybe this is what you're going to get to, can a transformer model very easily learn a PCFG?
So I would argue to your question that, yeah, it's too simple, those models, to describe languages, but it's still better than Gaussian or mixture of Gaussian. So I think we still need to move the field in one direction. And the point is to try to build a model which is still tractable. But you're going to my question. If you have a model like that, what can we say about how it's learned by DeepNet or transformers precisely?
Okay, go ahead. Thank you.
Other questions on the model? Okay. So the first question you could ask is supervised learning. If I have a deep architecture, which is trained knowing the class, how does it perform? So this is what we do. So if you look at this little figure on top, you have the generative model, you choose the class, and then you generate some data. At the end, the data, each symbol is converted in a one-hot encoding. So, okay, you make a vector in some space, Euclidean space. But then what you can do is train a deep net to reproduce this class knowing the data. It's just the usual supervised learning, nothing special there. And we look at it in the over-parameterized case. So we always have enough parameter in our architecture to actually fit the data. So if you want the training loss becomes perfect, becomes 0. But the question is, do you generalize? And we study that, it was nicely introduced by Geng, is in the feature learning regime. Initialize correctly so that it learns features. And here I'm going to go fast. So the result are that if you try to learn that, at least when the model is difficult, the model becomes difficult if you have many synonyms. What you find is that if you try to learn that with a shallow network, one hidden layer, so 2-layer network, it can't do it. So it is cursed by dimensionality. It needs an exponential number of data in the dimension. Okay. Now, you could ask, if I have a network that's deep enough, needs to be at least as deep as a generative model, then you find something very different. And we reported for CNNs and fully connected net in the paper. We checked for transformers. And we find that although prefactors can be quite different, they all have the same dominant term in a model like that. So they beat the curse of dimensionality. The number of the sample complexity, the number of data they need to essentially learn the rule is not exponential in the dimension. It's a polynomial in the dimension with some exponent A that you can relate to the parameters of the model. And what you can directly check, that's easy to do is that when this happens at the sample complexity, the network is building a hierarchical representation of the data. And the way we do it is to show that, for example, I don't know if you see my mouse, but here, if you look at deeper hidden layers, when you have enough data, those deeper hidden layers, they just encode for rather deep latent variables, and they don't care about, say, what happens at the input. And as you go deeper, you encode, if you want, deeper and deeper latent variables. So I would say that this model, it does capture the intuition that practitioners have, that DeepNet is successful, deep learning is successful because you build a hierarchical representation, but you can start putting number on this notion. So I have two slides to try to tell you, and it's important for what follows, where does this exponent A comes from, a simple argument for it. So how should you learn a model like this? Well, the key thing is to understand the structure of synonyms. It's high dimensional, but if you understand that, for example, these three things, H, I, G, I, and I are synonyms, and that they all code for D, and then you can, in this example, go from, a string of dimension 8 to a string of dimension 4. Okay, if you can do this grouping. And then you're dealing with the problem of twice smaller dimensions. So it should be even much easier to, again, find synonyms at the next level and understand its A, B, and so on. So it turned out that to learn those kind of models, indeed, it's the first step, learning synonyms near the leaf, which is the hardest. So how many data do you need to do that? So it turned out that the key quantity that controls when you can learn that, and it was understood already by Malak in a very interesting paper about not deep learning, but sequential algorithm, are the correlation between strings at the leaf and the class. So think about, for example, this GG location, and you can ask, well, if I look at this position, how much does that string correlate with the class? And the key point is that by construction, the correlation is going to be the same for synonyms. So it means if you have enough training sets and you can therefore compute precisely enough those correlation, in principle, you can group those strings together as synonyms when the correlations are identical. So that's the key idea. And the point is that you can actually compute how many data you need for the correlation to emerge from noise. Here, okay, I should say that you can compute it because you have random rules. This randomness of the rules allow you to compute the typical value of those correlations. And what you find is that the number of data you need to measure correlation beyond noise scales like M power L. Actually, there is a simple interpretation of that. So in this model, if you start from the class, say 1, and you go to a string like IG here, the number of choices you need to make is M times M times L. It's M cubed. In general, it's M power L. So one given path has many possible instantiations. What this is saying is that you need to see essentially all of them over the one to be able to start measuring correlation. And this number, if you convert it in a polynomial of D, give you the good answer. So it gives us the answer that we see in numerics. Another interesting aspect with respect to some of the literature is that it's not enough to be hierarchical. It's easy if the rules are not random to have a model which is hierarchical, but you purposefully build the correlation to be 0. And if we do that, you recover the curse of dimensionality. You need an exponential number of data to learn. This is just a counting argument. You can go further than that and show that in one step of gradient descent, you can group the first level of synonyms together and so on, but I will not enter into this. Okay, so I would, what time is it? Okay. I don't have time. It's good to have it. Okay.
You still have 20 minutes, more or less.
Okay, well, I'm doing pretty good. Yes, wait. Full screen.
10 minutes, actually, sorry.
Okay. So can we use this idea to think about self-supervised learning, mass token. So far, I just told you about how do you learn a hierarchical task, a function y of x, which is hierarchical. But I mentioned that the distribution itself is going to be interesting. P of x is going to be hierarchical. And so in particular, in a model like that, you can study what happens if you do next token prediction, just like what you do when you train ChatGPT. So a way to model this is, what if I give you many data like that and you play to train a model to guess what was, the last token here, this question mark. Okay, so from what I told you earlier, I think you can, if you are doing that with the deep architectures, in fact, for CNN and transformers, we find similar behavior, similar power laws, in fact. You will, okay, so what you will already realize that what's key are correlation. What correlations are really key? The correlations that are going to be key are not just pair correlation, it's a bit more complicated. There are the if you want multi-body correlation, there's a correlation between strings, for example, this GG here, and a token there. Because again, you can use those correlations if you have enough data to actually understand the structure of synonyms and start building a hierarchical representation. And when you build it deeper, you have even higher order correlations that play an important role. Okay, so we can make this quantitative. So you should be dealing, if I was honest, you should be dealing with this correlation, a string to our token. But in terms of scaling, if I deal with the token correlation, it gives me the same exponent. For the sake of simplicity, therefore, I will show you that quantity. So in a model like that, where you have a tree like that, what you find is that the correlation, token correlation, depend on space, and they decrease as a power law of the distance t between tokens. Okay, so in this curve here, what you should only see is a black curve. Okay, because my tree has a fixed geometry, you have a bunch of steps, but they oscillate around the power law. And this pairwise correlation function decreases like t power minus a, where a is the same a that I told you before. It's related to our parameters of the model. Okay, so you have those long-range correlations that exist in models like that, in tree models like this. But now you can understand what happens as you continuously increase the size of the training set. If you give me a bigger training set, you will be able to resolve to measure longer range correlations. And that's what's illustrated here. So again, in black, you have the theoretical predicted correlation. And what you see in color is an estimate of it for various training set size where you compute the correlation. So if your training set is only 100, you have such a poor, it's flat because you can't measure correlation, it's too noisy. But as you increase the number of data, you can start to resolve even long-range correlation. So the key idea here is that if you increase the training set, there is, if you want a given context, a larger and larger context where you can start to measure correlation and build a hierarchical representation. And it's easy to get. You just have to compare the signal, which is the correlation here, with sampling noise, which was like 1/√of p. And that gives me a scaling that relates the size of the training set. And if you want the context, where I will be able to actually build a hierarchical representation. So, for example, if you have a certain training set, you will be able to understand that HG, for example, really encodes for D there. But if you give me even more data, you will be able to understand that GG in fact corresponds to F, IH to E, and that EF to A. So you have this cascade of emergent phenomena where deeper and deeper representation are learned as the size of the training set increases. And this is something that in the paper, we tested for CNN and transformers directly at the level of representation. But for reasons of time, it also obviously has impact on the training curve. And that's what I will be discussing here. So this is this figure. Just look at one instantiation of the model. So let's say the blue figure. So this is the training curve. So the test cross entropy here as a function of the size of the training set. And if you look at those vertical bars here, that's where we predict that the number of data is enough to start learning the hierarchical representation at a deeper level, longer range and deeper. And what you see here as those horizontal lines are the optimal performance. So for example, this first horizontal line here is the optimal performance. If you really knew the model, you had learned perfectly and you're just given what I, for example, this stuff. Second plateau is optimal performance if you're given these three, HGI. And the last plateau here is if you're given everything. So, so thanks to that, you can compute how this training curve is behaving. And again, it's oscillating around this power law with an exponent beta that you can relate to the parameters of the model. So another way to test those ideas is to play with the context window, because normally when we train, we let the system know the entire data set, but instead you could just allow it to see, for example, I, the token next to the one you're trying to guess. That would correspond to the blue curve. If you have a context window which is 3, it means you're allowed to see HGI, and then your training curve is better, it saturates at the second plateau. If you see everything, it goes up to the third plateau. Okay, so essentially, this is the theory. It's making prediction on the training curves, on the effect of the context window, and on, how you should build hierarchical representation. And so in the few minutes I have left, I will tell you how we actually test it. So this is Shakespeare in the last iteration of the paper, like last days on archive. We also have Wikipedia. It leads to similar results. So you're training, again, next token prediction on Shakespeare. And in here, what you would see in, let's look at the purple T equal 15 would be the usual approximate power law tester. But now a qualitative evidence.
Are your tokens letters, words, or something in between?
They are not words, they are something in between. So Francesco could answer that in more details. He tokenized that. He's on the chat. So I will let him answer on the chat so I can go through this slide. So, so what you see here, which is qualitatively what we expect from the theory, is the effect of restricting the context window. So what you see that if you do restrict the context window, instead of your nice power law, you saturate, which indeed implies that the gain you have for larger P when you have a large context window come from the fact that you're exploiting longer range correlation. But now we can test that, the theory, more quantitatively. We can do a scaling prediction if we're given what is the correlation in the actual data. And for Shakespeare, we can measure the token-token correlation. And that's what you see in black here. Okay, so different colors are different estimate if you change how many data you use to, but let's focus on the large data limit. You find for Shakespeare a power law correlation of tokens, and you can measure the exponent A that enter there. So now if you follow 2 slides ago, I told you that there is a scaling relationship between context and size of the training set. It's just 2A, the exponent that enter in the scaling relationship. Essentially, this is saying that with the theory, we should be able to predict for a given context window, how the size of the training set P will scale where you start to saturate. Physicists, we like to put those predictions in terms of scaling functions. So it's essentially saying that if you rescale the y and the x-axis correctly, without fitting parameter, once you measure A, those curves should collapse. And this is the quality of the collapse we find for Shakespeare, and we have similar quality for Wikipedia. Okay, so this is my conclusion slide. So, so we introduced the model, this random hierarchical model, and in the context of supervised learning, what's nice that I think it captures results that are similar to practitioners' intuition. Deep nets build a hierarchical representation. The sample complexity is only polynomial in D. So in blue, I think that I'm emphasizing, questions that I would be interested to think about with the collaboration. And one aspect that we don't know how to treat. I told you that in this supervised setting, we can think about one step of gradient descent, but we don't know how to think about gradient flow or gradient descent in the entire deep net. But it's a very tough problem, but at least here in this model, we exactly know which representation the system is building. So I think it's a good model to start really tracking the dynamics and doing theory, and maybe the idea of Genghis and so on could be applied there, you know. Okay, it has also interest, for example, in this collaboration, we want to develop, you know, algorithm to characterize representation. We could benchmark them here. With respect to mass language models, so what we proposed is that those power laws come from a cascade of, if you want, emergent phenomena when you learn deeper and deeper representation. And that predicts scaling laws and relate them also tells you how the context window amplitude should enter in the scaling description. I think what something we're super interested about is we only can test in our group small models, small Wikipedia data and Shakespeare. So for example, we are not able to test the prediction on building a hierarchical representation deeper and deeper as, you know, the number of data increases. So we'd be extremely interested to collaborate, you know, with groups, Harvard or Montreal and so on, where we can have much larger models and really test those ideas. Then at the theoretical level, there are many extensions that would be interesting to discuss. I mean, so you asked that already. I mean, obviously the tree is fixed, it should be varying in geometry. We assume uniform rules, but for real languages, some are very rare and some are much more frequent. And also you have context dependence. Context-free is an approximation. So how do you go past that? Okay, thanks for your attention. I will take questions.
Thanks, Matthieu. Questions? Okay, Mazim has a question.
Yeah, thanks for the great talk. You mentioned this that shallow ones had this exponential complexity, and then deeper ones had this polynomial complexity.
Yes.
That in the context of this one step of gradient descent?
No.
So I have to say I'm pretty like I think that's kind of remarkable. Usually when I think about neural networks, okay, beyond depth 1 or 2, it's enough. You call it deep. Like there's usually not some abrupt transition at some large depth. So to some extent, I'm actually a bit skeptical that do you really have a sharp transition at some large depth?
Oh, okay. So I didn't say that. What I said is the case where we didn't study systematically as you change depth, you know, how, I mean, what we tested is shallow and deep enough. Okay, so deep enough, and we studied what happens when you go deep enough and even deeper. And we saw that deeper is just slightly improving that's the minimal depth. But we didn't
it has to be at least L.
So, okay, so let me just make completely clear what we've done. We looked at shallow and we looked at L or larger. We didn't really systematically study what happens in between. First of all. Second of all, so the statement is that when the problem is difficult, so in the model, it means when M is large, the statements are that if the depth is large enough than its threshold, it's moderately improving with depth. I mean, at theoretical level, essentially constant, and it's doing exponentially bad for L equal 1. But note that this is actually for the case where M is maximum, which means that you produce, the generative model produced all the possible data. And this task is quite brittle. If you change just one symbol, you can change the task. So if you make the problem simpler by reducing M, then you can find that a shallow network starts to do, okay, so we didn't study that theoretically nor experimentally systematically, but they do better. The same can be said about kernel methods. If you look at the hardest problem when M is large, usual kernels, even the NTK of a deep net, they need an exponential number of data to do the task. But if you are in a parameter regime of the generative model where the task is simpler because you don't have as many synonyms, then they can start to do a good job. I think there's a lot to explore here because this in terms of theory and so on, what happens if you're lazy and so on, I think that's very interesting. I can just report some observation at that stage.
Thanks.
Yazaman?
I guess my question was mostly answered in the last part. It was overlapping. I wondered if you could just conjecture a bit on the role of architecture on the sample complexity. Like, do you think this is kind of what you have is the best possible because it's only data dependent and something in between, or?
So what we studied a little bit was, CNN versus transformers and versus fully connected. And at the level of arguments, arguments don't allow to really distinguish between that. What we see that they all are all dominated by this factor I told you about, but they can have very different prefactors. Again, it would be great to have more theory on that. Yeah.
Can I ask a quick follow-up? So is the reason why you can't distinguish between transform and CNN because you don't have context dependence within, let's say, these leaf nodes?
So are you talking about the first part of the talk or
I'm basically trying to follow up with Yasama's question that whether, for example, CNN and you said the CNN transformers can't there's no distinction. Is the reason because in a generative process there is no context dependence, and one way that people say that transformers are useful is because there is attention to previous tokens.
Well, that's a very good question. What I can again state as a fact for those models is also in the second part, language model, we do explicitly compare CNN and transformers, because in the first part, the transformer part is not published, but if you look at the second paper, it is. You find very similar steps showing up at very similar locations. And so it's a beautiful question, the fact that, okay, cool. So if linguists, they believe that context-free grammar are a good approximation of structure of text for many languages, but also it's just for structure, for grammar. I mean, once you start to put semantic, it becomes an immensely complicated problem that I think they are debating and so on, where context dependence could be there and so on. So that's a beautiful question. I think it would be great for a group also to think about simple model where you start to, okay, linguists, they have proposed all those model tag where you play with trees to violate moderately context dependence. Context freeness, the fact that it's context free, they have some models where you break a little bit with that. And I think you're asking a beautiful question. So if we use transformers, can we see an advantage once it's not context free? And I would be super interested to discuss it or think about it.
Cengiz?
Thank you. So sort of following up on Bernd's question to me, is there a way, do you think, that the way you generate this data also has some kind of a power law structure in the covariance?
So let me try to. So what's the best? Maybe this is maybe the best. So what really matters in a model like that is more complicated than just the pairwise correlation. In fact, it's a sort of nested multi-level of correlation. So the fact is that if you assume that the data have a tree-like structure, you have power law correlation of the usual token correlation, and you see it on real data. So it supports that you should think about trees. But what really enters in the model is a bit more subtle because, as I mentioned, I don't know if I can write something, maybe not. So what I mentioned is if you want to learn a deep representation, what will arg? Okay, let's look at this GG. It's not the correlation between, say, G and the last token. It's between the string, first of all, to build. So if you want, it's a 3-body correlation or S plus 1 body correlation to first understand what is this latent variable. But then what the system will do is once it understands E and F, it will use correlation to group at the higher up level. So it's more complicated than just saying it's pairwise correlation that matters. I mean, when you have tree-like architecture like that, you have nested correlation, hierarchical correlations that exist.
Thank you.
Paul?
Thanks. That was fascinating, Matthieu. Thank you. I want to follow up on Yaseman's question because I was momentarily distracted where you were answering. I was thinking about something, and so I just wanted to make sure I understood correctly. She asked basically, I interpreted it as, you know, how do you know that you've got the best architecture to minimize the sample complexity? And, you know, of course, that was, and I was distracted because, you know, that was the thought I had early on, that we know the sample complexity is incredibly sample dependent. That's the whole point of having, as you said, CNNs and transformers. And I didn't completely hear your answer. Did you say you didn't see any architecture dependence of the sample complexity?
I will, okay, so first I will state just the fact that if you play with architecture, let's say for supervised learning, what you find is that when you change the architecture, the transformer and the CNN were doing more or less the same, and the fully connected net, which has no prior locality, was doing worst, but they are all their sample complexity. So the prefactors are very different, but the sample complexity, this term PEEP or A I told you about, is there always. So it's more about prefactor being very different. Working them out is a question for the future. Now, I didn't completely understand your point when you said that the sample complexity depends on the sample. I mean, I don't know in the sample.
Well, my point may have been incorrect based on what you just said, which is that, you know, you're looking at the scaling and it's just the prefactor. But do you believe that's the general case for these, you know, real language models, that the different architectures are just a question of the prefactor?
Well, first of all, I think if you're lazy or something, you will crash. At least in those models, it's not at all. But what appears to be quite generic is, yeah, if you're, I mean, at least for those class of model, is if you're deep enough and you're in the feature learning regime, then I would say that at first order, it's at least in those class of models, it's the same. Now, I wonder, actually, it's an interesting question for maybe, I don't know if someone will take the trouble for large language models where people optimize, if they would still, you know, try it with a CNN or something. I mean, I'm sure they have tried, but did they go, you know, put enough compute to actually measure exponent and compare?
I have one comment on that. I saw a paper at NeurIPS last year that was, I can't remember what data it was, maybe it was ImageNet, and they looked at the scaling laws for fully connected networks and convolutional networks, and the exponent was actually different.
What it was for what and what, sorry, for which?
They were comparing like the fully connected neural network architecture to convolutional neural network architecture. And they were just
the exponent, you mean beta, not just the prefactor.
Yeah.
Yeah. Interesting. I mean, yeah, if we are talking about training curve exponent, I mean, there are lots of works that focus on the prefactor in some sense, you know, also small index models and so on. And that's something, I mean, obviously, here, if you have a CNN, if you assume locality from the start, you get immensely different behavior. But typically, they are looking at more sample complexity and not train curve exponents. And then, obviously, you have giant differences. But yeah. I mean, this connects, what I'm trying to say maybe is that this connects to a literature which about single index or multi-index, where you assume that your function f of x is a function of, in fact, f of x1, or a few coordinates, and you try to prove to understand how neurons orient towards a good space, and become insensitive to the region where you don't have any, or where the task which is invariant for the task. And I think it's a very nice literature. One limitation is that, yeah, you're looking at a very specific model where so I think this question of locality, how do you learn how to localize neurons? You also have it in those hierarchical models. You can measure prefactors, but there is no theory yet. But I think those are interesting models to also understand how networks, because those networks, they eventually become CNNs. I mean, they learn locality, the fully connected nets. And that's what they do. And in fact, maybe that's going against your empirical observation. I mean, there have been works, I think, that shows that if you do pruning, or if you really have a huge number of data, assuming locality or having a fully connected starts to not play an immense role. Like you can learn locality well. I mean, that's a few years back. Okay, yeah.
Okay. If there are more questions, let's thanks again the speakers of today.
Matthieu, just a quick comment. I looked up the answer to my earlier question in your paper, and you actually did do it at the character level.
What, Francesco? Okay, so maybe it was character level. Francesco didn't reply in the chat.
No, I looked it up before he could reply. It's very clear. He said a million tokens.
Yeah, we would love to scale it up. I think we look at 16 tokens, so a few words, things like that, to really be able to, to really be able to, test about grammatical structure, hierarchy in that. I mean, what we could do if we have text is use parsing algorithm to just decide, build the parsing tree, know about this tree, and then see how the different sort of level of those trees are encoded in, your transformer or something like that. But to do that, we need to go much further than a few words. So that's, as our group, this is where we're limited. But I think as a collaboration, I think it would be beautiful to try to push in those directions. But I don't think it's something I can do just with my group, and that's why collaboration is. We need it. I mean, yeah.
Okay. So thanks again. Okay, I think we can wrap up for today. Maybe Mike has some comments.
Well, I mean, thanks. I think this was
Okay.
a very successful beginning 2 seminars, and I look forward to much more.
Okay. So we are planning to have the next one on next Thursday if we find 2 volunteers. So it's up to all of you. And if not, we need to postpone for 1 week. And there's also been a request for some people to have it starting a little bit later. And I propose to start half an hour later next times if it's good for the people in Europe. So if you have any comments on that, just send us an email. And with this, okay, let's thank everybody again and let's meet next week. Bye.
Thanks. Bye-bye.